Welcome back, everybody. So let's get started with the second one of those lectures. Looks like I've managed to scare off a lot of people by not talking about any math during the first part. So rest assured, after today, the slides will actually have a lot more math in it. I just wanted to first give you a bit of an overview of the context in which some of the machine learning algorithms run. And the reason why I believe it's important to tell you this is because it'll help you ask better questions. It doesn't necessarily help you find better answers, but it'll definitely help you with the questions. And yeah, by the way, who would like to see more math and who would like to see more pictures? So hands up for math. OK, hands up for the pictures. Now that sums up to more than the total number of people. OK, so I guess you want to see both, so we'll just do it faster. OK, good. Data flow paradigms. So here's the simplest way of parallelizing things. So you have a process by which you want to treat some data that comes in a stream, you do things with it, and at some point it goes out again. And you want to do this efficiently, so one way you can do is you just take the entire operation process, break it up into a set of filters, and then for instance you read from disk, you do feature extraction, you log things, you output it, and that's quite reasonable on a single machine, and you can actually parallelize that quite well. So each of us probably in the room here has a device that does this. It's like a phone. If you, for instance, record video, the video compression and the recording happens exactly this way. So any of those phones probably have the equivalent of 10 to 20 equivalents of a processor core in it, which sequentially deal with the data. And so if people nowadays talk about the dual-core cell phone, well, that's actually not really technically correct because they already have a video chip in it that has probably between 16 and 64 cores. And they have all sorts of custom special processing chips like for the baseband, for the camera and all that. So a lot of data processing can actually be accelerated by just breaking it down and then treating the data in a conveyor belt-like fashion. This is very simple parallelism, but it's actually really useful. It's particularly useful if you have some stages in there that are computationally very expensive, but they can be parallelized, or maybe an approximation of the algorithm can be parallelized. And so what you can do is you can just say, well, look, each of those processing stages maybe can be done data parallel, just as a filter, and then it moves on. And the Intel threading building blocks are a really cool device to let you do this. It's all open source, so you can use it. As a matter of fact, that's what gives you an extremely fast topic models code for a single machine. So this is our single machine parallelism, actually, as it happens. Another thing that you can do is, if you need to aggregate data, you can do it in a tree-wise fashion. Now, the good thing is this parallelizes at order log n cost if we do tree traversal, right? So if I want to compute the sum over all the numbers and I go through, then at each stage I have half the number of processing elements from before. It's really good. Communication is a bit of an issue because you need to actually at each step send the data across, and this is also great for data flow processing because then 2 to the n plus 1, if I have a 2 to the n fan in, is a good upper bound for the number of processing elements I'll need to deal with this. Fault tolerance isn't so amazing, and the other thing is this doesn't actually map so amazingly well into the server centers. So unless we can ensure that all the lower parts of a tree stay in the same rack, in which case it's sort of OK. Does anybody have an idea how we can sum over in numbers with n machines in less than log n cost, k times log n? So think about that for a while. I'll show you the solution to that shortly. So in order to get to the idea, let's look at an algorithm which initially looks, or a data flow strategy which initially looks amazingly stupid, right? So we have like one central CPU which aggregates all the data, and we have a lot of children, so it's just a star. So basically each of the leaves, it sends the data to the central node. Central node does its thing and it sends the data back. So if I want to compute the sum of a lot of numbers, if I set it up like this, I will have order n cost, right? If I have n children, if n leaves, then each leaf needs to send the data through, and then the poor central unit has to do all the work, and then it sends everything back. The latter maybe we can do with multicast, so that's easy, but that actually has cost linear in the number of machines. So can we use this idea to get an algorithm that is order 1 in the number of machines? Does anybody have an idea? Okay. Let me show you something that's a really useful tool as an additional piece of information, because we're going to make use of this. So suppose I want to have a distributed key value storage. So in other words, I have a whole bunch of key value pairs, and I just want to have like some cache where I send all those things to it, and you know, the more machines I have, the merrier, and it'll scale up linearly with the number of, you know, storage units that I have, and linearly with the number of, you know, well, basically it doesn't really matter very much with the requesters. So one way of going about this is I can distribute the keys, the key value pairs, among the caching units, and suppose they're maybe the purple ones here, based on a nearest neighbor hashing strategy. So what I do is I compute the hash function of a key and the machine ID. And I pick that machine that has the smallest hash value. Okay. So what this does is that it creates a uniform distribution of keys over machines. Because I pick the hash function, the probability of the hash taking on any specific value is uniform. This applies for all the machines, so therefore for each key it'll be a different machine. And so what I now do is I go and send the key to the machine that has the corresponding hash value. This means that if I have a lot of key value pairs, they're sent uniformly to all the individual caches. Furthermore, if I have two clients which want to access the same key value pair, they will both end up being directed to the same machine, to the same server, because the hash function is the same in both cases. Oh, thanks. So stuff like that is actually okay. Yeah. So stuff like that is actually implemented in memcached. And if you think, well, that's all kind of, well, sort of trivial, this is one of the key technologies behind, for instance, how Facebook works, and also how Wikipedia works. So in Wikipedia, for instance, what happens is the number of requests to view a Wikipedia page is insanely much higher than the number of requests to write a Wikipedia page. Right? Now, those Wikipedia pages are actually not stored in HTML on the server. They are stored as a structured database. So what happens is when you want to find out, for instance, about machine learning and you go to Wikipedia, it fires off a SQL query. It hits the database, extracts some data out of it, gets maybe some images and all sorts of other stuff. It then goes through an HTML rendering engine, and then at some point you see the stuff. Now, suppose that everybody here in the room decides to go to Wikipedia. Well, then, you know, we'll get maybe 100, 150 hits on the database. Well, this is no good. And especially the database is serving the same content over and over and over. What you can do instead is you get the data once, you then stick the machine learning and HTML code pair into that distributed caching service. This is done by some front-end server, and okay, now it's in the database. Next time, somebody else decides to view machine learning on Wikipedia, they first hit the cache, check whether the key value pair is there. If not, they go to the database. Otherwise, they just get it straight from the cache. And of course, what you want is you want to have a system where you can keep on adding more machines to the cache without taking everything else down. What happens in that case is I just increase the pool of machines that I have available, and then some keys that before that were hashed to another machine will now get hashed to this. Yep?
Maybe this is a little off topic, but do most of these methods, including MapReduce, with these key values, assume that the keys are smaller than the values?
Yes. Well, yes, you typically would assume that the key is just a key, not the content. So, for instance, keys that are quite commonly used would be a cookie. So, for instance, when you go to most internet services and they recognize you because some cookie was set on your browser. And when you show up, it pulls that cookie, says, OK, yes, you're back. By the way, here's your content. It might still request that you log in for operations that are more secure. So, for instance, changing passwords, it will almost always ask you for your current password before it lets you change the password. But it might already still recognize you. And yeah, so now what's really nice about this system is that we now get perfectly linear scalability in the number of servers. Because if I have more machines, well, they will just have another network interface. And since all the requests are sharded at random over all the servers, each server gets exactly a fraction 1 over n of the bandwidth and 1 over n of the requests. So this is perfect parallelism. And as long as we are not on too horrible network hardware, this is actually fine. So for the moment, we can assume everything sits on one switch. And peer-to-peer actually uses very similar strategies to find out where to store content. So if you use something like BitTorrent or Pastry, so they use very similar strategies for a distributed hash table. And we can go more into those details offline. Now, the nice thing about this strategy, as I said, is it scales perfectly. So can somebody already think of how we can add n numbers from n machines together, or I should make it more precise, n very large vectors from n machines in constant order one time? Okay, good. I'll show you the solution in a moment. But let me quickly show you a rather beautiful extension of this, what's called proportional hashing and caching. And so these guys here just got all from Yahoo, got the Usenix Best Paper Prize for that. And it's actually a beautiful paper to read. It's a bit lengthy, but it's very well explained, and I can just really give you only the very simple basic idea of it. Suppose I have different caches which have different amounts of memory. Or some requests are more frequent than others. So what you then want to do is you want to make sure that the caches that have more capacity get more keys, and you want to make sure that the really frequent requests are being served maybe by more than one machine, because you don't want to have hotspots. So this was actually in the context of serving video content on Yahoo. Now, one way how you can do this is by having the key space, the hashed key space, to be sparse, and each machine gets a range apportioned to it in accordance to the capacities of the machine. And OK, there will be some keys that are unassigned. And if I have a new machine, it just grabs some of this. And you start with maybe 1 or 2% of the key space assigned, and then you just add, and you fill it up, because rearranging keys is kind of messy, but it can be done. Now, once you do this, and you do the standard hashing trick, so you basically compute the hash of the key, you might end up with a key that's already assigned to a machine. Good, so we pick that machine, and that is, of course, uniformly distributed. That's good. Now, if I end up with a key that's not assigned to a machine, I just take the result of my hash and hash it again. And I keep on doing this until I hit the machine. This gives me a uniform distribution over machines. And furthermore, it's basically the first machine to hit is chosen. If at some point the machine dies, so I retire that corresponding key range, I'll just end up keeping on going and sending it to another machine. If a machine is added, I'll hit the cache earlier, so I'll end up caching things earlier. The net result of this is that by adding or retiring a machine, only a small number of data elements are affected that will now end up being cached in one place or not. That and a nice mechanism to ensure that if I have lots of requests, that it then is spread out on several machines, which I'm not going to go much into detail here, is what drives currently Yahoo's video caching architecture. And it's a beautiful paper if you enjoy this. And it's very easy reading. So strongly recommend it. Now, let me give you an answer to the question that I posed before. How can we sum over, n machines in order 1 time? So this is what I would call a distributed star. So remember what I said before? Well, we can have a star topology and we aggregate the data centrally. Now, what if I have a very long vector? I can go and break up this very long vector and send the first portion of this vector from all the other participating machines to machine number 1, and from the second portion to machine number 2, the third portion to machine number 3, and so on. Right? So I do this. Now, if I do that, it means that, yes, I have order n cost per portion. However, each portion is only size 1 over n. So therefore, the cost per machine is order 1. Because with n machines, it gets fragments of size 1 over n from n machines. The only overhead is really the cost for opening the network connection and closing it down. But if that is negligible to the amount of time that I spend on actually transferring the data and I have some mechanism for dealing with collisions, this will give me a mechanism for distributedly adding up numbers in constant time. And it scales perfectly with the number of machines involved. We'll actually use this for a distributed topic model later on towards the end of the talk. Right. So a lot of those models that I'm explaining to you right now, I'm not only explaining because they're kind of cool, but I'll also I'm explaining them because we will make use of exactly these very templates later on for designing algorithms that are very scalable. But the templates themselves, I think, are much more valuable, and I encourage you, when you think about parallelizing an algorithm, to look at these templates and think, maybe we can apply it. And there aren't a huge number of them out there, so it might be kind of handy to know them. Yes?
Once you compute the sum, how do you distribute? You just do a multicast?
OK, so very good question. Once I compute the sum, it basically means that each CPU has a fraction of 1 over n of all the data. Now, what you do again is you just reverse the same process, and each machine sends it to everybody. And so again, the bandwidth for each machine is order 1, and both incoming and outgoing. In some cases, you may actually not necessarily need to resync everything completely. Or actually what happens in one of the cases that we'll talk about, you will want to keep things up to date continuously. So basically, there will be a background job which does nothing else but just communicate. OK. Now, yep?
So I find it strange that you're saying that computation is order n, because you're assuming that you scale your number of machines available as you scale the size of the input.
Exactly.
Presumably you'll eventually run out of machines, right?
Yes, but if my goal is each machine has some data, has basically a vector, and the number of vectors is identical to the number of machines, and I want to sum them up and redistribute the average, that task I can do in order 1. So in this case, the amount of data is linear in the number of machines. This setting is more frequent than you would imagine. So for instance, in a distributed subgradient algorithm, you want to compute subgradients per machine and then sum them up. In this case, the dimensionality of the sufficient statistics doesn't really change very much with the number of machines, but the number of components that you need to sum together is linear in the number of machines. So if you do something like the bundle method solver, that's exactly what you get. If you do something like the dual decomposition methods of Stephen Boyd, Eckstein, and a few others, that's exactly what you get. If you do something like a stochastic gradient descent with subsequent averaging, that's exactly what you get. So that template is fairly common. And yes, if I have, of course, it completely fails if I have more machines than data, right? If I have more data than machines, well, no problem. It still scales. It's just that if I have more data than machines, it'll just take longer. There's no way around it. Any other questions? Okay, good. Then here's something fairly nifty, which apparently in some variant is in Torch. I'm not quite sure, but it's a really simple thing. So the issue is as follows. Suppose I'm in the single machine scenario, and you can easily imagine multi-machine scenarios accordingly. I read something from disk, I do maybe stochastic gradient descent, and it goes into memory, and then it goes into the CPU. Then a dumb algorithm would be the following. I read from disk, each item goes into memory, it goes into the cache, the CPU does something with it, it updates the parameters, and you keep on doing this. In this case, the algorithm will be I/O limited. So it'll be as slow as your disk. Okay. Can we do something better with it? Because during that time, the memory is really sitting idle, and the CPU is really idle. So a simple thing is, you have a ring buffer. Let me show you on a picture because video. Select source. Okay. So what happens is, so here's our disk, and here's the memory. Now I have a ring buffer. And so here's my read pointer from memory. And I can read 10 times as fast from memory as I can write from disk. So the disk has its own write pointer, and it just keeps on moving forward and overwriting old data. The read pointer from memory is going to go and overtake it occasionally, and it probably will jump over the location that's currently just being written, so I don't even need to lock anything. And it'll keep on doing this. So this way, I will process the same amount of data, maybe 5 to 10 times in memory, while it's coming in from disk. Why would I do this? Well, I can already argue it's not going to make things worse by just having a learning rate that's 1 over n, where n is the number of passes that I do for each part. But I might actually do a lot better if the data, especially in the beginning, if the data is actually fairly. I mean, quite often you would actually end up wanting to process the data maybe more than once in a stochastic gradient descent algorithm anyway. And so you basically end up, just being able to not have necessarily a completely IID sample, but something that looks sufficiently independent and seeing it 10 times. And if you have a lot of memory, let's say, 16 gigabytes or 32, that can actually store a fair amount of data as a buffer. And it's a very simple construction because now you have one thread which does nothing else but write. And it doesn't actually have to worry about other things, but just record its write position occasionally. And the read operation, which does nothing else but just read. When it does the read, it checks, okay, what's the current write position? Since it knows it's going to be faster anyway, it can just aggressively read up to here and at some point make a jump. And it makes for very simple code. Because you've completely decoupled the disk I/O and the memory I/O. And it paralyzes. On top of that, you could think of a similar thing if you have a CPU and it has its own cache, that I basically now read from memory into the cache. Same thing happens. I could actually even have a network here. And maybe the network is much slower than my disk, because maybe that's an SSD. The same thing. Now I basically get a sequence of ring buffers that I chain together. And this way, I get the maximum processing throughput here. Okay. It's a very simple design strategy. We have yet to prove that this is actually doing something really good, but it looks good so far. Okay. Set to screen. Okay. Now, summing things up, I think I showed you a little bit about what hardware things run on, processing paradigms, and data flow. Now, let me give you a bit more motivation in terms of the applications, why you would care about this. So this is really the one slide that has a lot of it in it. Data on the internet. And this is a grossly incomplete list. Let's just go through some of the things. So this is something that everybody knows, right? Web pages. When we talk about the internet, usually that's what we mean. So you have the content, but you also have the graph. However, what you also get is a lot of click data. Because people click on ads, they click on pages, they recommend things socially to each other, and you get clicks accordingly. There are the users themselves. So they have some IDs, maybe a Facebook Connect or whatever. They have profiles attached to them, locations, whatever. Emails. Well, it's both the content of the emails, when they send what to whom, and of course to whom. Photos, movies. So Flickr, YouTube, Vimeo, and so on. They actually store a lot of content here. And I think we're barely scratching the surface of content analysis on video. Cookies and tracking info. So if you don't know how much is going on in your browser, I strongly recommend that you install Ghostery on your machine in Firefox or Chrome. And it'll show you all the tracking that's going on. And so you would wonder, why is this happening? And what you'll see is that there are some websites which have maybe 10 different tracking systems simultaneously enabled. Okay. So, for instance, if you go to my homepage, you'll see there is, Quantcast, and there's also Google Analytics. They will give you information about who goes to which site, when, how frequently, what the number of users is. It comes up with estimates of their demographics, their age, their income, everything. So it's actually quite interesting. So for me, this is more out of vanity and just to see what's going on. If I were in the business of selling things, like, for instance, a machine learning software package, then I would care about this very much, because I would see, OK, these are my target users. So if I, for instance, know that people in Silicon Valley with an income over 100K usually come to my site, well, I would target them. I would start advertising on places where such people congregate. And maybe this way I'll get more customers. And this is why a lot of places offer this service for free for users. So this is, for instance, why Google Analytics offers free tracking, because they get the data too. On top of that, of course, you get information about which browser things are running in and all that. And this gives you information about page relevance, about ads. It allows you to track users between different sites. And if, for instance, I know that you've been to maybe DP Review, which is a camera site, and then afterwards you've been to Ritz Camera, I know that probably an ad for Adorama, which is also a camera site, is going to do really well with you because you like cameras. So if I can track you through a few places, I can send you more relevant ads. And I think the worst thing about ads is really if you get irrelevant ones. If the ads are on target, it's, I believe, less annoying, and I think it's a necessary price for getting a lot of services for free. So this is cookies. Now, installed apps. Well, I can actually do a lot of recommendation based on that. So the App Store Genius feature, for instance, tries to do something like that on iOS. Not claiming it's terribly amazingly good, but they try at least. Location. You can do a lot with that, and so Latitude, Google Latitude Looped or Foursquared, they all provide such services. Also Facebook local check-in, Yelp check-ins. Now, if I know where you check in, I know what other places you might like. I can use that data directly myself to monetize it by showing more relevant ads, or I can actually just sell it to somebody else who does something useful with it. So be careful what toolbars and other stuff you install on your browser. Toolbars are usually or synchronization features or whatever. They might do something useful, but most likely they'll also send a lot of your usage data back to some server. So always look at what these things are doing. Maybe I shouldn't say that because that's actually how we make money, but yeah. Then user-generated content. Well, there's a lot of data there. I mean, Wikipedia, there's also associated content, which Yahoo, for instance, just bought, which is a way how you can basically write articles and maybe get a few cents for it. Ads, well, first of all, what they look like. So they are display and text ads. So DoubleClick and Yahoo are some of the major players there. Quantcast, Efficient Frontier, Contera. There are a lot of places which work on that. Comments, discuss Facebook, for instance. Reviews, well, Yahoo Local, Yelp, opinions, a lot of reviews are there. So what I'm trying to show you is that the amount of data, the types of data sources is really massive. You might actually get third-party features. So Experian, for instance, sell credit ratings based on IP numbers. Social connections, so you can get the graph maybe, maybe not. So Twitter, for instance, really doesn't like it if you crawl their graph. Purchase decisions, so Netflix knows a lot about that. So does Amazon. So does a few mail providers as well, because they get the receipts, right? Instant messages, so Yahoo Instant Messaging, Skype, Gtalk, MSN Messenger, AOL, whatever. Timestamps go with essentially everything. Search terms, Google and Bing. Well, by now, all our search goes to Bing, yeah. You might wonder, why doesn't anybody release queries? Well, this happened maybe about 5 years ago with AOL search. And it cost the guy in charge of it his job. And the reason for that was that somebody managed to identify themselves based on the search terms. This is also one of the reasons why the Netflix 2 dataset was essentially pulled. It's quite sad that even if you try to anonymize things, quite often there might be 1 or 2 people among the set who manage to identify themselves. Like in Netflix, some woman believed that this would out her as having a sexual orientation that she wanted to hide. By going public with this, of course, I mean, she did exactly the opposite, but being rational is a different thing. But yeah, so you won't be able to anonymize everything perfectly anyway, but you just try to do things at least in a reasonably nice way. I mean, it gets dangerous at the point when a human starts to look at this data and figure out that, for instance, well, some specific person has a specific interest. As long as you have global targeting algorithms, I believe it's still, at least I personally find it less dangerous. Yeah, news articles, well, you want to actually have relevant news that you show people, blog posts, microblogs, there's a lot of them. So all those things are data sources. These data sources don't necessarily come with a specific machine learning problem attached. And in many cases, you're probably better off combining more than one of those sources to solve your problem. At which point, most of the very clean machine learning problems that you will see during the summer school will fail. They will fail because the assumptions are not satisfied anymore. Because you don't have independent, identically distributed data. Of course not. You have data maybe with some geolocation, with time, and all sorts of other things attached to it. In which case, you need to be careful about your modeling assumptions, and you need to do reasonable modeling before you can solve the problem. So don't just go and say, ah, okay, this looks like a classification problem, so therefore, yeah, okay, this is fine, I can just use it. Look at what people have done in these very clean prototypical cases, and then adjust them accordingly to actually fit your problem. Okay. A few other things is resources are finite. So editors cost a lot of money, and they don't really know the users anyway, and you usually can't get an editor in every language. So this is why you should be very careful in using editors. Yeah. Abuse. Well, in some cases, you know what spam looks like, and that's good, and you can build a spam filter. But abuse is usually the thing that looks like something that you haven't seen yet. I mean, basically, whenever a new virus comes up, it is successful because it does something that nobody else has thought of yet. So the only way to get around this is to have a novelty detection algorithm. Now, they don't guarantee that they'll pick everything, but it's better than nothing. In many cases, you don't have explicit feedback. So, for instance, wouldn't it be nice if all of our users were to actually go out and label their email and say this is spam and it's not spam? Most users don't label even a single thing. The other thing is data analysis rather than, so quite often you're given the data set and it's like, let's do something interesting with it as opposed to, well, here's a specific problem. And a lot of the work is the modeling work until you get to the point of, by the way, here's an estimation problem I want to solve. You need to integrate several systems. That's why you want to design modularly. And, well, you know, this is really what you should also do. Invest a lot in modeling. OK. So that's just the very high-level view of data on the internet. And you have basically as much data as you could wish for. So here's a couple of examples of pretty good unsupervised modeling, and we'll be looking at the mathematical background for that soon. This is a very nice example of hierarchical clustering. It's not a huge data set, 50,000 images. And they basically have a hierarchical Dirichlet process to do the clustering. And these are images from some database. I think it was Cypher or something like that. The funny thing is you might ask, you know, what is the picture here on the very top, which is like the most prototypical image? And yeah, it turned out to be a lawnmower. Here's something that it's a very famous example from 2003. Basically, you want to get topics within the text, and the various colors correspond to a few topics. You can get that with latent Dirichlet allocation. We'll see that a lot soon. Word segmentation. It's a nice paper by Mochihashi and et al. So they took this and basically asked what are the, so to say, statistical breakpoints between sequence elements. And this is what you get as a fully unsupervised segmentation. There was no prior knowledge in this. And you can see it gets it wrong, like the long, right? Or of the. The reason is because the long and of the are sufficiently frequently occurring terms that it makes sense to compress them as one. And you would probably see the ing in a few places being here separately, because ing also occurs quite often as, you know, just a character sequence on their own. And then BBIT, yeah, that's from the rabbit because it's from Alice in Wonderland, as I guess you all could tell by now. This uses a very nice infinite Markov model. It's a nice paper. You can automatically use that to synthesize data. It's actually from the same paper. And the key point is this is all automatically generated. It looks about the same informativeness as a Federal Reserve press release when they don't want to say anything. So it uses actually these as fragments, which it observed somewhere, so it pieces them together like a jigsaw. Here's something that we did. If you go to KDD, you'll see it. So basically what we did is we tracked users. These are two different users. And first of all, we automatically determined what the various interest types are. So the only thing that's human-generated are the names here of these topics. So I guess most of us will agree men, women, dating, singles, personal, seeking, and match might map quite well into dating. Or for instance, Snooki, Tom Cruise, Katie Holmes, Pinkett, Kudrow, and Hollywood. Celebrity is pretty good, and so on. And so the interests are normalized to sum up to less than 1. This is number of days. And you can see somebody who's fairly interested in dating and maybe a bit celebrity. And at some point, he's not so interested in dating. All of a sudden, he's interested in his health. OK, make out of that whatever you want. At some point, he's heavily interested in baseball. And, well, maybe dating isn't quite so cool anymore. This guy, diehard baseball fanatic, at some point realizes he's out of money, right? Like a week and a half later, he starts looking for a job. Now, the point is, this is real data. We didn't make this up. This is one of many millions of users. Now, imagine what you can do with this in terms of advertising. Right? OK, that's why we do it.
So he didn't identify himself from that graph and complain?
I would think these graphs are very typical for many users. And yeah, we're working on things that will give us this in a more detailed and sophisticated manner. So for instance, one thing that you're going to miss with this is, suppose we had a photography topic. You won't be able to tell whether I'm a diehard Nikon or Canon fanatic. And for instance, my cameras are all Canon. And if you show me a Nikon ad, I'm going to ignore it. It's just because there's no point, because I already have all my lenses and everything for Canon. And equally, they're diehard Nikon fanatics. And they will not switch. So if I show you the wrong ad, it's wasted. And that type of content, you're not going to pick up with course topics like this. And that's actually currently an interesting open research question. Yeah, of course, this is when you want to show the ads, right? That's quite a beautiful paper by Andrew McCallum and co-workers. So what they did is they basically said, well, look, there are all those images of people on the internet with captions, but of course you don't quite know who is who on those pictures, so you just have a list of people who might or might not occur, and then you need to find out who is who. And they did a pretty good job at you. So this is what they get with people LDA, and it's hard to believe that these would be actually classification errors. I think this is one of the Williams sisters, or maybe that's her sister then, God knows. So it's pretty good. Something that we did, storylines from news. So we took a news stream. We identified the topics, like in this case, sports, politics, unrest, whatever. These words are all automatically extracted. Then these are particular storylines. That's their frequency over time, like tax bills. And you can see that Bush Senate, US Congress, Fleischer, and so on. It's a bit older data. And here, tax billion cut, and so on. But these are actually all quite closely topically related. And then you can do interesting things like say, well, look, I want to find something that's also that's similar to India-Pakistan tension, but maybe, and has also nuclear in it. And lo and behold, you get the US and North Korea issue, for instance, out of it. And if you just want to have the tension, you get the Middle East, right? So it's, OK, I'm not interpreting this. You can detect ideologies, and again, I'll talk a bit more about that later. Here's some hypertext topic extraction. I think there's some better recent work out there which uses the links a bit more intelligently. That data set worked on Wikipedia with 2,000 pages, but it's a fairly well-cited paper. OK, a bit more on supervised models. You could, for instance, get ontologies. So there's DMOS. There's a few problems there. I mean, you need to continuously maintain it. You don't really get much guarantee of coverage. And the categories are human-generated. So avoid if you can. Right? By the way, I think I'm running out of batteries here. If somebody has 2 AAA batteries. Yeah. I mean, it's still OK, but at some point I'll probably let's hope it lasts. OK, so This is the problem, right? 90,000 editors, 1 million categories, 5 million sites. So on average, 5 pages per category. Not good. Face classification, that's one of the larger face databases by some Iranian university. God knows why they were interested in it. Topic detection and tracking, there's a lot of things annotated. Actually, by now, our unsupervised algorithms beat the best supervised one, which is kind of fun. Advertising targeting. So if you look at ad solutions or the Google categories for that, I mean, you basically select, do I want to advertise in games, computer, video games, and shooter games? This, by the way, is what Google thinks my interests are. This is utterly wrong. I'm just not interested in it. This is correct. This is pretty wrong. Sports news, not really, not at all. And this is utterly wrong. So that's it. It gets about half things right? And this is probably good enough for advertising. And you can slice things different ways. For instance, with ad solutions, you can, aggregate accordingly, and maybe this is more meaningful than this, maybe it isn't. God knows. But the problem is advertisers like this stuff. Because quite often there's a human interface, and I think that human interface actually often should be best avoided, but that's just how business is done. That, somebody says, well, look, I think my customers are affluent people. Okay, so I want to advertise to affluent people. Okay, so you need to have something that maps it into reasonably well-defined user categories. Collaborative filtering is an obvious case of supervised learning. They just went public, Pandora. Then there's Last.fm, Amazon, Netflix. And an interesting thing is actually that quite often you don't only have the recommendation problem here, but you also have a social network between them. And I think this was last year at WWW we showed that if you use both data sources, you do much better in each of those cases, which is a complete no-brainer, right? Basically, it's exactly using homophily, namely similar people like similar things, and people who like similar things are probably more likely to be connected. Okay, simple insight. If you use it, you do better. So it's not a very pure classification or recommendation problem, but it's several of those problems tangled together. And if you build a model that can actually deal with this, you'll do better. Okay, so bottom line, you have like a lot of data, millions to billions. You have a rather rich structure of the data. And the model, the overall aggregate model, will typically not fit into a single machine. So this is an important issue. So your parameter vector, your weight vector, will often not fit into a workstation. So you need to find ways how to partition, how to distribute your model, such that maybe the most relevant bits very well fit onto every machine, but then you have further adjustments per machine. And do not just blindly use something like clustering, classification, or topic models, because that's probably not going to solve your problem. Just because you've read a paper that does this and applies it to dataset X does not mean that applying algorithm A to dataset X is a good idea. Try to find out what the problem is that you're trying to solve. I'm saying that because I've seen it happen too many times the other way around, and then I get emails like, oh, by the way, I used your algorithm and it doesn't work on my data set. And then I ask them, what on earth did you do? And it turns out that the first thing I tell them, don't use my algorithm. Use something else, something much simpler maybe. Right? So that's why it's actually important. So we have essentially an infinite amount of data. Labeling is quite often prohibitively expensive, and editorial use is not really good. So the only thing I can really do is I can show you building blocks, and then we go into further details. Now, I can go into basic tools, and we can probably get through some of Statistics 101. But before that, I should probably let you ask a few questions. None? Okay, good. Statistics 101. Okay, this is really simple. And have you guys seen this thing before already in like day 1 or 2 of the summer school? Okay, like you have a space of events. You have the probability axioms, like the probability that something happened is well bounded between 0 and 1, and the probability that something happens is exactly 1. If I have disjoint sets, then the probabilities of each of those events can be summed up, right? And you can get things like, well, the probability of a server working is 99.9%. However, you also get interesting things like, for instance, for the income, I need to specify a range. Can somebody tell me why it's a stupid idea to ask, what's the probability that I earn, let's say, $91,322.15? Why is this a bad question? Yes, exactly. So here I have a density. And the fact that it's a density means that point queries for probabilities are nonsensical. I need to actually define a range that doesn't have measure 0 in order to get somewhere. Okay. Then this is the usual thing with the Venn diagram, right? We have all the events. And so the probability for the union is the probability of one plus the probability of the other minus the intersection. Independence, well, the probability of x and y is given by the probability of x times the probability of y. So for instance, the login behavior of two users is approximately independent of each other, except, for instance, suppose Vishy and I are good friends and we are somewhere together and we, after dinner, both decide to do something on our computers, then the login behavior will not be independent of each other anymore. So on the other hand, I mean, one thing that you would hope for is that the disk crashes on different colos is approximately independent. Can somebody tell me why disk crashes may not be independent?
Might have been bought at the same time.
Exactly. So I had that once, 5 out of 12 disks failing at the same time. Yay. I think Vishy, you still remember. Yeah. So, however, if I condition on the fact that I bought them at the same time, then they become independent of each other. Because then I know all of them are going to fail exactly after 42 days, right? So dependent events, emails, for instance, might not be dependent. Queries, the news stream, IM communication, also Russian roulette, right? So the probability of the bullet firing the next time will depend on whether it's already fired or not. Okay? And it's basically everywhere. And this is a good thing. You usually want to have dependence, because otherwise observing X doesn't tell you anything about Y. And finding out when to approximate things as being independent and when to approximate them as being dependent is quite important. If you screw up that part of the modeling, you have a problem. So to drive the message home a little bit. So suppose your wife gets pregnant. You want to find out whether it's a boy or a girl. So you go to some, highly reliable source of information and you ask her, well, is it going to be a boy or a girl? She looks into her crystal bowl and maybe behind her back tosses a coin. Oh, okay, it's going to be a boy. So she does that with equal probability. However, let's also assume that boys and girls occur with equal probability. Then those 4 events, each of them are easily given by just factorizing things, right? So, in other words, the astrologist gets it right in half of all the cases. Now, here's what you would do with a slightly more reliable source of information. You go and ask a maybe medical practitioner, and he might say, okay, well, it's, you might get it right with 90% probability. So that's 0.5 times 0.9 gives you 0.45. And obviously, these are the cases you talk about, whereas with the astrologist, these are the cases you talk about. For the rest, you're too embarrassed. Now, here's a simple graphical model based on this. Say we have spam. So I decide whether I want to send you spam or not. And then I write an email for you. So I can write that P of spam in male is P of spam times P of male given spam. Okay, what have I just done? I've just basically used Bayes' rule. So the joint probability P of x and y, I can write it as P of x given y times P of y, which is also by symmetry P of y given x times P of x. Now I just use that equality and solve for P of x given y. That's nothing else than P of y given x times P of x divided by P of y. So that's an extremely powerful thing. If that's the only thing you remember from the 8 hours, mission accomplished. Okay, so let's use that. Okay, so before I show you the answer, I want to get some estimates from you guys. So let's suppose 0.1% of all people are infected, and I have a test that's very highly reliable, and it detects all the infections. And suppose it actually reports positive for 1% of all healthy people. What's the probability of having AIDS if the test comes back positive? Any numbers? Okay. 9%? Okay. Any other numbers? Who says 90%? 90? Who votes for that? Who votes for 50%? Guys, you're all just looking at the slides. So here's what you get. So P of test, given that somebody has AIDS, so this is really where we use Bayes' rule. So we want to get the probability of the AIDS test of somebody having AIDS, given that the test comes back positive. So that's P of the test coming back positive, given that somebody has AIDS, times the probability that he has AIDS, divided by the probability that the test will come back positive overall. Now, I don't have that number, but I can compute it by just looking at the probability that comes back positive if he has AIDS, plus the probability that he comes back positive times the probability that he doesn't have AIDS. Okay? So that's 1 times 0.001 divided by 1 times 0.001 plus 0.01 times 99.9%. And that's 9% basically. This is amazingly counterintuitive, right? So, you would think, you do have an AIDS test done and it comes back positive. It's a real worry. A lot of medical doctors don't know probability. So I don't know who of you was in a situation where they had to have some blood tests done. The physician might actually recommend you not to do it because you might be too worried for a false positive. Happened to me in my case, and I just asked the guy, so what's the probability and so on, and his eyes just glazed over. Okay, so yeah, people have actually been convicted of crimes based on poor probability. Okay, now let's improve that diagnosis a little bit. The test comes back positive. I mean, you need to do something about it, right? So you have a second test done. And that second test is worse than the first test. It's worse because, it only reports positive for 90% of all the infections. And it comes back positive for 5% of all healthy people. And suppose that test is also positive. So then I get now something that's like 36%. Mind you, it's still less than 50%, but it's a lot worse. So here's a question. Why can't we just go and use the first test twice? After all, it's a good test, right? Any ideas? Well, they're not independent of each other. If I repeat the first test, it'll just give me the same result again. Why can't I actually use the second test? Because I hope that conditioned on the disease status, the outcome is independent. Okay, that's what it is. So if I'm basically assuming that P of T1 and T2 given A is P of T1 given A times P of T2 given A. Yeah. So just a quick aside, and Sergey starts at 2, is it? Okay, so that means now. So I need to stop here. Let me just finish with that one slide. and we'll do naive Bayes in the next lecture. So this is really important if you implement anything dealing with probabilities. It's sufficiently important that a lot of people screw it up. For instance, if you look at Mahout, it's actually screwed up in the Dirichlet process clustering. And most people will make that mistake at least once in their life. So here's what happens. If I deal with probabilities, and multiplying probabilities together will make small numbers really small. They'll make the numerical underflow. In other words, I multiply two small numbers together, all of a sudden things are 0. Bad news. Because now if I divide by something, a small number by another small number, I get division by 0, and my computer blows up. If that doesn't happen, at least I will get so god-awful rounding errors that the numbers are not reliable anymore. So what happens is that I'm basically using the exponent where I should have been using the mantissa instead. So here's the thing. I use 1 bit for the sign, I use 11 bits for the exponent, and 52 for the mantissa. That's for an 8-byte floating point number. For 4 bytes, it's even worse. Now, if everything is stored in the exponent, well, how can we move it from the exponent into the mantissa? Right? That's basically the goal. Well, the way how to do this is you just take logarithms. And now small numbers aren't quite so small anymore. However, what it means is that the multiplications and additions have to change. Where I had a multiplication before, I now get an addition. That's good news. That's actually faster. However, if I had a sum before, I now need to replace it by this operation. So what I do is basically, so I replace p by pi. And now the sum over pi becomes max of pi plus the log of sum over e to the pi I minus max of pi. Okay. So here's what happened. I basically take the largest probability and divide everything by that largest probability. That's what max of pi does. So because pi I minus max of pi is basically just the log of the ratio between them, right? And I need to exponentiate because I need to sum in the end. But now in the exponents, everywhere I get small numbers. And I know that there's exactly one term in it that is equals to 1, and all the other ones are smaller. So now this is numerically well conditioned, and I can do this. So if this is news to you, and you ever work with probabilities, remember this. Please do. OK. So now I best pass on the mic to Sergey and let him continue. And we'll do naive Bayes next time.